The last class we saw about the Newton's laws of motion. Okay, and the Newton's laws of motion. Why it is important is because before Newton's laws of motions were proposed, what were people following? It was Aristotle's fallacy. Okay, where it says for uniform motion there has to be a constant force, which has been corrected by Galileo and then followed by the Newton. Okay, what it says, Newton's law says is a motion. Okay, every body remains to be in the state of rest or in uniform motion if there is no external force acting upon it. That means if something is at rest, okay, and if something is at motion, they both are identical. What it says is in both the cases there is no force acting on it. Okay, that means what? There won't be any acceleration. So this is important. Why in the sense is, so for example, so you are having a frame. You know what's the reference frame? Okay, what's the reference frame?
Reference point.
Yeah, you associate a reference frame within myself. Okay, so what am I going to do? I am a reference frame. I will see, and I will see many bodies are moving around with me. I don't know what they are. So many. I'm going to associate my reference frame, the moving body. Okay, so some reference frame I will see that is moving at a constant velocity. Some frame which is at rest. Okay, so I can say these frames are at rest. So I say there is no force acting on it. These frames are moving at a constant velocity. So there is no force acting on it. If anything is accelerated, then I say there is some forces acting on it. And now, so what I say, for me, there is some frame, some reference, some object which is at rest. That's with respect to my frame. It won't be same for another person. So suppose another person, if you have a different reference system, and in his reference system, if I am moving, okay, for him, the object won't be at rest. Okay, what Newton's law says is it doesn't matter.
Okay.
They all are one and the same. Okay, what it says is if you are moving in a bus at a constant velocity, okay, you see your co-passenger is at rest. For an outside person, you are also moving, the co-passenger is also moving. And what the thing is, if you measure your weight, the mass of the object in that bus, as well as if you measure your mass in the other person's frame. Okay, so what happened? You measured your mass in the bus. You got some 45 kgs or 50 kgs. Now you came out. Somehow you came out and came in rest. So now you are in the other person's frame. Will the mass be different?
It will not be.
It will not be. It will be same, because the point is all quantities measured in the inertial frames are going to be same. On the other hand, let us say you are in a lift. Okay, the lift is moving down. Do you feel a kind of a weight reduction in the weight? And when it's moving up, you feel a kind of weight is increased. If you put a weighing machine and you stand, you will actually experience a difference in the weight. Okay, and you know, because you know that okay, you are moving in a lift, and because you see from outside. Suppose if I put you completely in a closed chamber, you have no idea, and the lift is a very smooth lift, no vibrations. You never know what you are actually moving or not. You feel that you are at rest. Okay, but you see your mass is different. Okay, so will this frame, the lift frame, is it inertial? Is that will that frame is you can put in a Newton's law of motion? Newton's law, because that frame is accelerating. You are to the gravity. Okay, for that, so your quantities won't be same there. So any frame which is at rest or which is an uniform motion, all the measurements is going to be same. Not just measurements, even your laws of physics, everything will be identical. So those frames, the collection of those the frames means reference system. The coordinate system, we call it as a frames. Okay. Those reference systems are called as the inertial frames. Why it is important? Newton's law says in those reference frames, your laws of motion are simply described by the three laws. Okay, and they will change only if any of the frame is having an acceleration. Okay, so that's why, for example, okay, you can say you take a projectile motion. You did a projectile motion. Am I right? So in one frame, you take a projectile motion, you'll be seen. Suppose you are saying this frame is at rest. You did a projectile motion there. Now this frame is moving with a velocity v. And now again, sitting on the frame, you throw the stone. Both is going to be same. Okay, you are in a bus, you are in a train, constant moving train. Okay, and there is no vibration and anything. You can play the cricket as if you are playing on the ground. Okay, because the laws are going to, because both the frames are basically inertial frames. Okay, unless until the train is vibrating or shaking or there's acceleration. If it is moving in a constant speed, and if you're in a complete enclosed chamber, you don't know what is there. So then you won't realize, are you in rest or are you in motion? So you are actually in motion. You can play the entire game as if you're playing on the ground. Okay, so that's what you are. So all this is what your Newton's law says. So all these frames, which are in a uniform motion to each other, means moving at a uniform velocity. The laws of physics are same, and even the quantities, if you measure the quantities, they all are going to be same. Okay, so those frames are called as your inertial frames. And the moment, if there's an acceleration, any of the frame is accelerated. Okay, if any of the frame is accelerated, then your second law says there has to be a force applied to it. Okay, and once a force applied, then that frame is no more an inertial frame. So that frame is called as your non-inertial frame. Okay, as you said, okay, the lift, which is moving down in gravity. Okay, so is it inertial frame or non-inertial? Non, because the gravity is there. But now, let us say, for example, I have closed you completely. You don't know. Okay? And you are saying you are in the lift and you can see your weight has increased. But there is no force literally acting on it. But there is a change in the quantity. You got it? Because your weight increase means you are having a more attraction. There is something pulling you down at a rate more, right? So then there is some force, but you don't know. There is no force is there. So that force will come through. That's called a pseudo force. Okay, because it's a pseudo force is because there is not a real force acting on you because your frame of reference is accelerated. Okay, you are in accelerated frame, so you will experience a force. That's called a pseudo force. But a pseudo force is not an imaginary force, a real force. Okay, because you can measure your weight. Okay, so this is what your inertial frames and non-inertial frames. Okay, non-inertial frames are one which the frame is accelerated. And the point is accelerated, and then when it's an accelerated frame, your Newton's laws of motion will not be valid. So there again, your what you call. So those frames are called as your non-inertial frames. Now, can you tell me? Suppose I have two frames. Okay, I have two frames. This is a frame 1. Let me call it as frame A. I'm having another frame, which is I'll call it as frame B. Okay. So this is at rest. So this is moving at a velocity v. Now, for this frame, there is an object. This object is moving with an acceleration a. What will be that acceleration measured by this frame?
The acceleration of A with the acceleration of B, the original acceleration.
But is this frame is accelerating? It's moving at a constant velocity. Will it be accelerating?
No.
So what will be the acceleration?
Only the acceleration of A.
This body, this frame also will measure the same acceleration as the acceleration. Okay. Will measure the object's acceleration to be same irrespective of the frame. Suppose, for example, this body again in this frame, it is moving with a constant velocity, say some v1.
Okay.
Okay, so what the object's velocity measured by B frame?
It will be at rest. Not rest, but it will be the same.
It will be same because they both are moving in the same direction.
Huh.
So then, for this guy, this object will move with the velocity at rest.
No, uniform motion, right?
Correct. Both are all in uniform motion.
Huh.
These both are in uniform motion.
Mhm.
This is at rest. This is a constant velocity.
Huh.
So for this frame, there is an object. For respect to this frame,
Huh.
this object is moving with a velocity v1.
Huh.
So what will be for this frame?
So it will be same velocity v1, right?
Will it be same velocity v1 or
No, it won't have any acceleration. So
you are in a bus moving with a velocity v,
Huh.
and there is a ball. In the bus, you throw a ball with a constant velocity.
Huh.
Throw a ball. After some time, the ball has attained a constant velocity is moving.
Okay.
You are having a velocity v,
Huh.
and in the velocity, your frame, there is a ball which is moving with a constant velocity.
Huh.
For an observer outside,
Huh.
who is at rest,
Hmm.
will the velocity be same?
No, it won't be same.
How much it will be?
Okay, it will be addition.
Addition of those two. So of course, why it can be, how it will be same? You got it? So this person, he is going to measure the velocity as v1, whereas this person will measure the velocity
V plus
of this
V1.
as v plus
V1.
v1. Okay, so the velocity gets added up.
Huh.
But the acceleration
will not get added.
won't be same. Why the acceleration won't be same? Let us say, for example, if this is a v1. Suppose if the v1 is changing with time.
Okay.
Okay, so then if it changes with time, there's a rate of change of velocity.
Acceleration.
Rate of change of velocity is nothing but acceleration, right? So if it changes with time, then you have acceleration A will be equal to dv1
By D.
by dt. By dt. Okay. So now for this person, what is the velocity here? See for this source, for this object. This is the velocity of this one. Okay, v1 plus the velocity of the frame. Am I right?
V. Huh.
So now for him to, you want to find out the acceleration of this object.
Okay.
What he will do, he'll take a d. This is the total velocity he measures, right? So let me call it as what happened. Let me call it as give me u.
Okay.
Okay, u is the velocity of the object measured by this frame. So now you have to find out what is the acceleration of this object. So what is going to do? So acceleration will be du by dt. Am I right? That's the acceleration we're going to measure. So now what is u? v1 plus v. So d by dt of v1 plus v. Now that is equal to what? dv1 by dt plus dv by dt. Okay. Now this is moving at a constant velocity. So derivative of a constant is
0.
0. Okay. So this goes to 0. So this will be what? dv1 by dt. Isn't it the same acceleration of that person? Okay. So that's what. So the acceleration is not going to change. So whatever because when it's acceleration, that means there's a force. So I'm going to study this object. The acceleration happening on the object because of the force and everything. Okay. And that, whatever the study I'm going to do, that's not going to change if I switch to another inertial frame. Okay. Now we understand the concept of inertial frame. Okay. So this is a frame which is moving at a constant velocity. All the frames which are moving at a constant velocity or at rest doesn't matter because there's nothing like a rest. Because the rest corresponding to you may not be a rest to some other frame. So all you have to say is all frames which are moving at a constant velocity. The acceleration measured is going to be same. Correct? The acceleration what you're going to measure is going to be same. That means that's what the physics, laws of physics and everything is going to be same in all these frames. Those frames you call it as your inertial frames. Got it clear now? So inertial frame is the one. The frame which are moving at all the frames which are moving at some constant velocity. Suppose if I am here, all the frames, and I said no, all frames which are moving at a constant velocity to me. They are inertial frames. How many such frames can be there? Infinite frames. Okay, so every frame there can be infinite inertial frames. The moment any frame is going to have an acceleration, Then what happens? So this is also going to be a time. Am I right? When it becomes time, this won't become 0. Okay? So, yes, so this will
different accelerations.
Yes, so this acceleration will be, then in that case, my both acceleration is not going to be same. Add up. No, it doesn't add up. Okay, I can see. We never know that. We got to just calculate. So it is not going to be same. The acceleration measured by this frame, which is moving frame, the acceleration measured by this frame is not going to be same. Therefore, those frames are your non-inertial frames. Okay, and your physics laws of motion cannot be applied there directly. Okay, we can apply. What you do is you have to apply a pseudo force. We will see that what your pseudo force is. Well, then later on you will understand. Okay. Pseudo force means there is no real force. What happens? That acceleration, if there is some acceleration is there, somehow I have to cancel the acceleration. I give an opposite force.
Okay.
I assume a pseudo force. So in that case, when I assume a pseudo force, that means I have actually accounted for the acceleration. Now I have taken a constant velocity. Then now again I can use my equations, whatever laws of physics I can use it there. So that's what your pseudo force is. It's not a real force. Okay, but it is not imaginary force. Means that's why I say when you move in the lift, you will feel that you can measure your change in the weight. So there's a real quantity. It's not an imaginary quantity. Okay, but there's no force acting on it. Because you are in a closed frame, you never know, but your weight is. So what happened? That force is pseudo force. Okay, you have to cancel it, then only you can do the the laws of physics you can apply on it. Okay, fine. This is what your frame, inertial frames and the non-inertial frames. Okay, so now. Okay, so now the question comes. Let me go to the next topic, which we will do it today or tomorrow. Okay, let me finish up some of the. Okay, other part I'll go. So I'll finish up whatever the written on this book. Okay, so in your book is you mentioned it, but it's not very clear. Certain things are. Usually, a set of coordinates with a suitable origin is enough to describe the frame of world. Okay, yeah. Okay, means a set of coordinates with a suitable origin is enough to describe the frame of reference. That's the frame of reference. If the position coordinate of an object continuously changing, in that frame, if a position coordinate of a charge is changing, then you call that object is in motion with respect to that reference frame. That's important. Any frame of reference in which Newton's first law is applicable is the simplest understanding of an inertial frame of reference. I explained it, right? That's right. Fine. This is all okay. Thus, in an inertial frame, a body will move with a constant velocity if there is no net force acting upon it. That's whatever Newton's law is. You'll get satisfied there. Fine. This is important. Measurements in one inertial frame can be converted to measurements in another inertial frame by a simple transformation. I showed you. Okay, the velocity will get added up. Of course, acceleration is not going to be different. It will be changed. It will be same. Okay. By simply using some velocity vectors between the two reference frames. That's why I showed. Okay, fine. Yeah, there's one illustration they given which is not very clear, but you can still imagine yourself inside a car with all windows opaque. Okay. That means you can't see anything inside, so that you cannot see anything outside.
Okay.
Also consider that there is a pendulum tied inside the car and not set into oscillations. That's a pendulum. Okay. If the car just starts its motion, it sits at rest. So that means you already given force. Okay, you got it? You never know. Because you are not given any force. So from the outside is given some force. Okay, so this is going to give you a jerk. Okay. You will experience a jerk. That is acceleration inside the car, even though there is no force acting upon you.
Okay, pseudo force.
Yeah, this is a pseudo force. Okay. During this time, the string of the pendulum, I don't know, maybe steady but not vertical. Yeah, something like that. It comes out, jerks out, something like that. Anyway, I don't know what they mentioned. You are given a force, pseudo force acts upon it. During the time of acceleration, the car can be considered to be a non-inertial reference frame. Okay. When you get a jerk, then the car is, force applied, so there is a non-inertial. Okay. Later on, if the car is moving with a constant velocity, after some time, the car starts moving with a constant velocity. Now your frame is in a reference frame.
Inertial frame.
Suppose if your pendulum is hanging there, it will be as if
It's not.
the car is at rest. Okay, and when you oscillate a pendulum, you get all the periods and everything. The same thing you will find when the car is moving at a constant velocity also. That's what. Okay, but there, I don't know, in a book they written it a very, I don't know, later on the car moving at constant velocity, you will not experience any jerky motion within the car. And the car can be considered as inertial frame. In this case, the pendulum string will be vertical when not oscillating.
Okay.
It remains like that.
Straight.
Okay. Fine. So this is what. Okay. So this is important. Do you know the situations or phenomena that can be explained using Newton's laws of motion fall under the Newtonian mechanics?
Okay.
Okay. This is all inertial frames and everything. This is what you call as a Newtonian mechanics. Okay. And Newton mechanics is not a complete. Okay. So why I will come? I will come because so far, but to a day-to-day life. To day-to-day life, whatever you are dealing with it, this all can be handled with your Newtonian mechanics. Okay. And the moment, if you are, means, okay, under very strong force, okay, when the force becomes extremely high, okay, or the velocity becomes very high, then the Newtonian mechanics fails, and then you get what you call as your relativistic motion, relativistic mechanics. Okay, so that's what comes in our see. Newton mechanics is perfectly applicable in our day-to-day life situations because there's not much of motion is there. However, under several extreme conditions, we need to use some other theories.
Okay.
So, what are the limitations of Newton's laws of motion? Newton's laws of motion are applicable only in the inertial frames of reference. If the body is in a frame of reference of acceleration, okay, we need to use a pseudo force in addition to all other force while writing the force equations. Okay, so now, so if it is acceleration is there, I have to first apply a pseudo force to nullify that force, and then I have to write down all the equations. This is another problem with that one. Second one is Newton laws are applicable for point objects. This is very important. What do you mean by point objects? It don't have size.
No.
The size of the object is zero. Okay, when I say a mass or something, the object size is zero. Okay. And well, the next point is comes to there itself. Okay, the object size is zero. That means the point one. I mean, it doesn't matter it's a car or an elephant or aeroplane. For Newton mechanics, everything matters. It's a point. Later on, you will see that point can be easily as the center of mass. Okay, so that you will see. You already read about center of mass?
Center of mass, yes.
No. Last year, 10th standard, you read?
I know of it, but I haven't read of it.
Okay, you will see. Possibly you may reach in your later classes, you will find out. Okay. And the next and third spiral is same thing with that. Newton laws of body apply to Newton laws of applicable to rigid bodies. Rigid body means what? Not on a balloon, water balloon or something. The body means the 2 points. Yeah, it remains the same. The distance between 2 points in the object, they remains same always. Okay, so that's what. The body is said to be rigid if the relative distance between its particles do not change. For any deforming force. There won't be any deformation on this one. Okay, and then, yeah, and this is important. For the objects moving with speeds comparable to that of light. Okay, Newton's law of motion do not give the results that match the experimental results. Yeah, and the ancient special theory of relativity has been used. Okay, you will see later on. All these Newton's laws of motion is actually incorrect. Incorrect, totally incorrect description. The correct description is given by the ancient relativity. And the more correct is the general relativity. Which considers your acceleration. Acceleration of the field you will later on in the higher classes you will see that. Okay. Yeah, and this is another one. So what happened? So actually this I'll say. And the next one is the behavior and the interaction of objects having atomic or molecular size. When you go to smaller sizes, again the Newton's law fails and what you have to use is a quantum mechanics. Okay, so the Newton's law fail when you go to the objects of high masses. Okay, high masses mean like a black hole. Planets also happen. Yeah, but it won't be that visible. Once you go to a black hole or something, then this in the vicinity of a black hole. Nothing work. Newton's mechanics will not work there at all. Okay, you can't add up any pseudo force, nothing will work out.
Okay.
Okay, there it is what happened. Your because of a strong gravity, the attraction stronger, the bodies will start moving with a velocity close to velocity of light. So then the entire mechanics change. Okay, it's not even special relativity; it is general theory of relativity that you will understand. You will study it in your higher classes when you okay. So for heavy masses also fails. Now you go to the subatomic particle.
Okay.
Going to electron, proton, nucleus, molecules, atomic structures, their motions between those bodies are so that also is not defined by your Newton mechanics. There it comes with your quantum mechanics.
Okay.
So what it says is Newton mechanics is not a complete description of your mechanics. Okay, rather the more complete description is the Einstein's. Okay, so that's it. Anyway, that doesn't go into the quantum mechanics.
Okay.
Quantum mechanics is completely different one. Okay, so this is what about your mechanics and inertial frames and other things. But okay, for your class, you are going to deal only with the inertial frames and Newton mechanics. Maybe in your later higher colleges, you will find out you will go through the you will go to relativistic mechanics also. Okay, fine. So I'll stop here. In the next class, we will discuss about the types of forces. When I ask you about the types of forces, you will say, how can I say there is a lot of force? I kick a ball, there's a one force. I drop a ball, there is one force. I blow a balloon, there's a one force. What do you mean by types of force? Okay, now the whole question comes is, yes, there are many forces around. We say, how do you say force? Anything which causes acceleration. Newton's law said there won't be any acceleration if there's no force acting on it. If anything causing an acceleration, that means some force is applied on it. Correct? So now, can you unify all the forces? It was an important question. Whether all the forces are a manifestation of a single force. Okay? Or these forces, there are forces which comes out, you can't really equate, they both all are same. Okay, so that gives us two types of forces. Okay, so we will see that forces in the next class. Okay?